All right, so we've talked about two major classes of problems. They're derivatives of each other, I suppose. The second one includes the first. So we've talked about diffusion problems, and we've called it force media flow, but it's basically a diffusion equation, a second order term and a zeroth order term in space and first order in time. And one in which we've added to that a term which relates to advective fluxes. And so, as you all know, the basic problem that we've been dealing with has been, I will do it using this terminology, is something that relates to, say, concentration, an advective velocity, and an advective flux, and some component related to time, capacitance. And so when we talked about flow problems, the parts of this expression that we needed were the first and the last. This was hydraulic conductivity, this was head, and this was time, and there was an extra term there, but it was basically the same equation, a diffusion equation. And when we wanted to deal with mass transport, when we're looking at mass flux carried by a carrier fluid, motion of a carrier fluid, then we have an extra term which relates to this advective behavior. And so we've really talked about this one advection diffusion solution. The first stuff was just where the advective term was zero, but there you realize, of course, that they're basically the same expressions. We know how to solve them both linearly and for steady state and for transient behavior. When we solve for transient behavior, this term now is no longer zero, and we have to accommodate it. And we solved them using a variety of time-stepping methods and talked about the spectrum of time-stepping methods. So we know a fair bit now about this expression. The final part in talking about mass transport is to talk about reactive transport. And so that refers to the case where transformations may occur during flow or by interaction with the porous media. And it's a relatively straightforward process to add in that it can be added in three different ways. We can add it as some kind of pseudo sorptive behavior where components get removed from the flow field and attached to the solid substrate which the fluid is flowing past, and therefore is lost to the flow because, of course, maybe we haven't said it explicitly, but the concentrations that we're talking about are concentrations in the fluid. And so if some of that material is taken out of the fluid and put on the solid and therefore is no longer mobile or no longer in the fluid, then it is a net loss to the conservation equation, the mass conservation equation. So sorption is one process that does that relatively straightforwardly. We can also accommodate first order reactions relatively straightforwardly, which is where you have, for instance, dissolution or precipitation acting to be able to dissolve material from the porous media or to precipitate material that's in the aqueous phase onto the solid. And we can also talk in terms of multiple reactions that occur within the fluid as well. And so the two main ones of these that we'll deal with, and then give some examples of them, I think using COMSOL today, if we get to it, are to look at sorption and to very quickly maybe look at multiple first order reactions, but then the main one is to look at multiple reactions. In your notes, they're slightly backwards, so this is what we'll come back to. We won't worry about that now, but we'll talk first about these three methods I just mentioned here. And so maybe this is a good table of contents to come back to, but I don't think we necessarily need to go through these things. Let's deal with them in sequence. First with the idea of reaction being taken care of by a pseudo-reactive approach, which is really retardation or sorption. And it revolves around the very simple notion that if you take a a beaker full of beads and or quartz grains or sorbent, if you like, solid sorbent, activated carbon, if you like, and you put in contact with that a solution that has a particular concentration, then you expect a certain proportion of that material in solution to be taken out of solution and put on the solid. It sorbs onto the surface layer and is held there. When the aqueous concentration is reduced, then it will desorb. It's a reversible process. In other words, if you then take the aqueous concentration that's attached to this down here, then you'll actually only have this amount held on the substrate. And so it's a equilibrium behavior. You apply it, it doesn't necessarily happen instantaneously, but the sorption isotherm is after you've waited for it to occur at its maximum sorption capacity. And if you do that at a variety of different concentrations, aqueous concentrations, you might get a straight line, or you might get something different from that. But the straight line is basically an isotherm. It's what you'd know as an isotherm. And if you look at this advection diffusion equation, then all of these terms, since we're adding them to each other, they all have to have the same units, obviously. And they have units of mass per unit volume per unit time. I guess I'm mixing my units, right? So I guess it's mass per unit volume per unit time, or I guess this would be mass per unit volume per unit. I don't like to use T because uppercase T we'll use for something else. So MLT systems is what these are. And so physically what that means, this is a rate of change of mass in a given volume of fluid per unit time. And the mass is not mass of the fluid, of course, it's mass of the dissolved aqueous components. And so you can think of this as a rate of change of mass per unit volume per time. And so if you wanted to accommodate this, you could account for the mass that's removed by sorption per unit time to be placed on the substrate and then made immobile. And so what you could do is take our standard advection diffusion equation, which are just these first terms, and add an extra term plus or minus, which is due to the mass that's lost in the system. And the mass that's lost in the system can be defined in terms of this isotherm as the density of the aquifer, the porosity of the aquifer, time change, and the concentration, the mass that's sorbed on solid. So this isn't a mass, but it's a concentration. It's a mass per unit mass of the solid. So it's a mass of solute sorbed onto per mass of the aquifer, if you like. And of course this equation isn't homogeneous in terms of the same concentrations. And so what we can do is we can take this concentration that's written in terms of the mass sorbed per unit mass on the aquifer and just rewrite it by doing what we did before, just multiply it by 1. And that 1 happens to be concentration in the aqueous concentration in the aquifer. And so if we do that, now we have an expression that was written in terms of the mass on the solid, but now it's an expression which is written in terms of the rate of change of concentration in exactly the same way as it's written here, but multiplied by a material coefficient. And this material coefficient is just the gradient of this line, right? This is concentration, aqueous concentration. This is solid concentration. The ratio of those changes is just 1 over. So this is going to be equal to a change in concentration. This is going to be equal to, bless you, a change in solid concentration. And so the ratio of these two is just 1 over KD, 1 over KD. And so what we can do is we can resubstitute this back in here. And now all of a sudden it's written only in terms of aqueous concentration. And if you manipulate this, the final result that you get is just a dispersion advection equation, which has a pre-multiplier, which is referred to as retardation coefficient. And so the retardation coefficient has a physical meaning that it retards the transport of that species. And the easiest way to think about it is almost as a scaling magnitude. If you look at a flow along the length of a core, how far that pulse has gone in a given time, then what retardation does, it takes material out of the aqueous phase, puts it on the solid phase where it's immobile and no longer in the water, and therefore it retards the propagation of this front. It does a couple of things actually. It means that this front is retarded. It doesn't go so fast as the advective velocity in the system because it's gone less far in a given amount of time. And also, just by virtue of the fact that you're removing material and putting it on the solid, it also sharpens it. So it's not by accident that the slopes of these fronts are slightly different, is that the effect of this behavior is that it sharpens the front. So and you could rationalize that that's the case merely by taking this new expression. So this is density of the aquifer, porosity, and a material property. If it's a big number, it means it sorbs a lot of material on. It would be activated carbon. If it's a small number, it would be something that doesn't sorb very much, like quartz or something. And so the larger this number, the larger difference there is of this left-hand term from 1 to be larger than 1. So if you divide both sides through by this value r, just by dividing both sides, and this is r over r, of course, then you see this behavior that you'd expect would drop out. It has two important effects. One, it makes this velocity slower by the magnitude of this retardation factor. And it also effectively, since this number is always bigger than 1, it makes this diffusion coefficient smaller, this effective diffusion coefficient smaller. And so the physical meaning of that is that it becomes more advective, and so it just becomes a straight front that moves through the system. And so that's one way of dealing with these kind of reactions as a sorption behavior where you're physically removing material through the system. Of course, if you then flush this system with water, the material that you had sorbed onto the grains would actually backflow out of the system to recover. And so that would be, it's a reversible process in that you're able to move up and down this line as you change concentrations in the aqueous behavior. So it's reversible. And this is just one linear isotherm to represent this behavior. Of course, there are many, many different forms of isotherms. So that's one way to be able to deal with this. The second way to deal with this is to be able to write this term. So it all revolves around the fact that when we have this advection dispersion equation, the behavior defines a rate of change of concentration with time as a mass loss to the system per unit of volume of the aquifer per unit time. So this is really a reaction rate term that's present within the system. And so if you can define what the reaction rate is in terms of some other physical meaning, then you can also substitute for this magnitude. And so one way to think about that would be if you're net dissolving, say, quartz or any other mineral for that matter from a system. So the rate of change of concentration that you dissolve into a system would be the magnitude of the local concentration within the fluid relative to the equilibrium concentration. Equilibrium concentration, by definition, is where it's at equilibrium, so there's no net exchange between one phase and the other. So if you have an equilibrium concentration as your fluid is flowing, then this term by definition is 0, and so there's no exchange either taken out of the fluid and precipitated onto the solid, or dissolved from the solid and put into solution in the flow field. So when this concentration is either side of the equilibrium concentration, in one case you'll have dissolution, in the other case you'll have precipitation. And you can accommodate both of them. And so this, of course, not of course, but this is a material property. This rate constant, dissolution rate constant, is also a material property. And so the only variable in this is actually the concentration, aqueous concentration in your system. For instance, as you dissolve or precipitate quartz. You dissolve quartz and make it in aqueous form. And so if you substitute this expression into, substitute for this term here, then we could perhaps guess what this term would come out to look like. We don't know what that is. We know that when we transfer from a differential equation to get to a finite element equation, we know that we do certain things to the individual terms. They all have some characteristic form, right? What do we know about this? We know that this term is something like, what is it? It's an integral over the volume A transpose dA dV. I guess actually we haven't talked about this per se. We know that this term is something like integral, again, over the volume of the shape functions, B transpose B, again, over the volume, and a concentration change. And I guess this operates on a concentration as well. And I guess it would be multiplied by 1, or R, if you wanted, some material property. I'm trying to think what this one is. This ends up changing the sign from a negative to a plus, but what is it? It's integral over the volume again. Is it B transpose, shape functions transpose, velocity, and I think it is. We should tell. Actually, why didn't someone check? It's either AB or BA. I think it's this way. And so that says something about what we'd expect this, right? So we have a 0th order term in space, 1st order in time, 2nd order in space, I guess 0th order in time, and 1st order in space and 0th order in time. And so these are characteristics expressions that will always represent those behaviors. And so if you have a 2nd order behavior, when we look at solid mechanics, we'll find out we have exactly the same matrix to deal with in here. The derivatives of the shape functions, a different constitutive law instead of diffusion coefficient, it will be Hooke's law, but nonetheless it will actually be the same. And of course we'd have different nodal variables, they'd be displacements, which are vectoral quantities rather than scalar values. And so the reason for doing that is the question then is, what does this look like when we have to deal with this concentration term? Well, it's 0th order in space and it's 1st order in time, and so it's just going to look exactly like this term here. So it's going to be integral over the volume B transpose B dV. And it's going to be multiplied also by concentration rate of change. And so it will be this term here will slip down to be able to define this behavior. So if you, in other words, if you substitute this dCdt term in that we have here, that's represented here, then this coefficient, I suppose, just has to be something like minus k times nodal values of concentration minus the equilibrium values of concentration, which might be the same at each node or might not. It depends on what you want to do. This is a material property, this is a material property, and this is a variable. And I guess since it's a rate of change, no, actually it's not a rate of change, right? This was a rate of change, but now it's just a pseudo steady state which is occurring. And so that's exactly what you see below here. So in other words, capacitance term, dCdt, diffusion term, advective term, and then finally this exchange term between an immobile substrate and the aqueous material. And so you just have to then figure out how to be able to rearrange that into a system that you can solve. And that's what's given below. So capacitance term, diffusion term, advective term, and this exchange term. If you want to solve it in time, you have to figure out exactly what you might know in all of this. Is that right? Yes. I think, yeah, is this actually right that it does this? This is a concert. Yeah, I think that's right. It's not wrong. That's not right, is it? Haven't looked at this in a while. These aren't over dots. And so the component that would go in here is a magnitude. Part of it is an unknown, particular time step. And I suppose you could actually assume that you got this from the previous time step, and you can compute this magnitude of flux and just balance this equation by taking this whole expression off to the left-hand side. So, for instance, you could include this. You could do it two ways. You could include this expression at time t, and you could combine it with this expression here, and move just this off to the left-hand side. Or you could just move this whole thing off to the right-hand side, and you could use the concentration from the previous time step to be able to solve it. No, you could do either one of these. So I think this is the way that this is written might be. Is it right? I'm trying to see if it's. Concentration goes on this and this. Yeah, no, this is right. Yeah, this is done right. So this is the right. So this is just the magnitude operating on the concentration as a function of time. Okay, and so that's the method of being able to do it. So both of those are kind of imperfect ways, maybe, of dealing with this, and not as sophisticated as using the third case, where we have these multiple interacting solutes. And so for that, there is an explanation following this, but the most compact explanation, I think, is the one that exists on this page here, for looking at multiple reactions. So let's mess around with that, and then also then implement it in COMSOL. Go and visit COMSOL and seeing how to use that. So this is our differential equation written for our system with capacitance, advection, diffusion, dispersion, and a reaction term attached to it. We're adding apples to apples, and so all of these have the same units by definition. And if we want to generically represent the case where we have a first-order reaction where we add two components to get a third component, we can look in terms of the reaction in terms of two ways. It reaches an equilibrium when the rate of production of C is exactly matched by the rate of production of AB in the reverse reaction. And so it never actually stops, but it reaches a steady state because the counter magnitudes of the reactions basically counteract each other. And so we can define the forward rate of this reaction as being some coefficient multiplied through by the concentrations of each of the species, A and B. And the reverse rate of that is a different coefficient multiplied through by the concentration of the product of those reactions. The two components and then the ultimate product. And so typically we can represent these reactions, well, we could represent them as kinetic reactions, which we're not going to talk about in this class, but we can also talk about them as equilibrium and their march to equilibrium as controlled by the spatial distribution of concentrations in a flow field. So right now these are reactions that are in the aqueous phase, so it could be in a beaker, it doesn't necessarily have to be in a moving fluid. So this could just be a reaction that's in a beaker, that's a well-stirred beaker that's having these reaction coefficients. But if we look at equilibrium, then when the forward rate is equal to the reverse rate, then the concentrations of these individual components overall, on average, is not changing. And we can write that behavior in terms of this, just equating these two forward and reverse rates to get this expression. If we rearrange the magnitudes of the reaction rates, then we can calculate the magnitudes of these concentrations that we get as a function of these reaction rates. So in other words, we can measure K1 and K2 are just individual properties. Should change this, because this is the way this is actually wrong. This is backwards, I realized. So it's worthwhile changing these rates. And this is also, as a result, backwards. But the other calculations, it's easier just to change this than change some other things. And so what we can do is, since we know that if we start off, so we can follow a system, and we'll use this just to validate our own system. If we start with a mole each of A and B, and nothing of C, then we know that if we define the amount of C that we have in the system, component C, then since the overall fraction, molar fraction of the whole system has to be A minus B. Yeah, so if you have A minus B, so A and B goes to give a certain amount of C, and the amount of C we call X, and the total molar amount, since we have 1 mole of A and 1 mole of B in the first place, and so it's a mole of each of these, not 2 moles, but 1 mole of each of these, then the amount of A and B that we have at equilibrium has to be the initial amount, 1 mole, minus the molar amount of C that gets produced. And so the total amount of this that we have in the system of A on its own and B on its own is 1 minus X. And so to have the two of them, we have 1 minus X squared, which represents the A amount, which is 1 minus X, and the B amount, which is 1 minus X, and the C amount, which is X. And so if you solve this expression, we know that from this, the ratios of these have to be given by K2 over K1, which is 10 over 1, this. And if you solve this quadratic, you end up with magnitudes. You can substitute it in here, that the amount of A, which is equal to B, which is 0.916, and the amount of X, which is C, has to be this. And you can show that, right? It's going to be 0.916 all squared divided by 0.0839. And so 0.916 squared, I think, you can do the calculation, is 0.839. 0.839 divided by 0.0839 gives you 10. And so it works out. And so those are the equilibrium concentrations that we'd expect after the reactions have come to some steady state. And so we can use that, and we will use that, to be able to look at the system of equations where, if we want to solve this now, we can write one of these expressions for each of the species that we have. So in this particular case we have 3 species, but we actually only have 2 independent species because A and B are, we could think of them as the same as each other. And in fact we defined them in terms of A is really 1 minus X and C is equal to X. And so we know that B is equal to the same amount, so they'll mirror each other. So what we could do is we could write this equation 3 times. So I guess I could write it. So in other words, rate of change of concentration for species A as a function of time is, I'm just going to write out the same expression, del concentration of A times U minus del bracket D. And this would be the diffusion coefficient for A if it was different for anything else. Del CA actually turns out to be useful, is equal to RA. And this RA is given by these magnitudes of these concentrations. So these would be the concentrations. This would be the concentration A, which is equal to the concentration B, which is not equal to the concentration C, right? This is different. And so what we can do is we can write a rate expression which just gets added onto one of these for each of these expressions. We could write the same expression for the second one, but it would be identical, and so we actually don't need to do that. And so instead we could then write it for the third one. So it's just going to be concentration of C changing as a function of time, as a function of concentration C and a velocity, minus the derivative, diffusion coefficient of C, del operator Cc is equal to this. So we have two expressions that define this behavior. So there are two effects going on. There's this reaction rate, which could be happening within a static beaker, which doesn't really need anything of this, and we can do the calculation for the progress of this reaction. Well, it's a steady reaction, so we're only dealing with its steady state. But of course, as different amounts of this molar amount of material come into play within the flow domain, then the equilibrium concentrations that work out will also change as well. And so it'll only be equal to these two ratios for the static case. But let's go ahead and try and use this to be able to solve a relatively straightforward expression using COMSOL. And so what we'll do is you notice a couple of things. Well, the first is that we need basically one equation for each species in general. We're going to get away with less than that because we have two species that are in the same molar proportion. These A and B are going to be identical. So we can get away with this third equation we don't need. To solve the system, we need to do something with the reaction rates in this term. If we really want to solve a flow system, then the other thing we have to figure out is the magnitude of this velocity, which is included in both of these things. So we're starting to get, I guess now is the first time that we're starting to layer these things over each other. We have a beaker with this reaction, A plus B equals C. We can solve that just by the reaction rates, and we get this single value, which is what we have here, and that value won't change. It's a steady value, it's an equilibrium value. That's one part of it. If instead of being in a beaker, different components of A and B are being supplied in different concentrations, then that will give different equilibrium concentrations of C in different locations of our aquifer. And so to solve that, we need to be able to solve these two expressions simultaneously. And to be able to solve these expressions, we need to have the magnitude of the flow field and its spatial distribution to be able to calculate what the advective velocities are, which then affect reaction rates. And so that's kind of the web that we're trying to put together here. So let's go ahead and put together an example of that. The other thing, I guess, I'm not sure we have time to talk about it. If we do, we don't. So this is the general expression to represent this behavior. Doesn't really matter for now. But the other thing is that reactions can be exothermic or endothermic. And so depending on what heat is generated, you can define those heats as a function of the reaction rate, which we calculate here, the heat rate, which is a function of the reaction, to give a total amount of heat which is put into a system. And I guess we haven't really covered heat flow yet. But you could also couple this with the amount of heat that would be generated to push this away from just uniform temperature by solving the heat conduction equation with thermal conduction, thermal advection, and thermal capacitance, where if you know what the reaction rates are, you have a chance of being able to figure out exactly what the magnitudes of these, the heat input or output, the heat put into the system or the heat extracted from the system by the reactions would be as well, in which case you'd want to solve for the heat flow equation. So in terms of the hierarchy, we have a flow field we have to solve for. Once we have that flow field, we know what the flow velocities are everywhere in our system. Once we have those flow velocities, we have enough to solve for both of these expressions. And included in this are the right-hand sides, which are these reaction rates, which we're solving for as well.